All right, welcome to the deep dive. Today, we're going deeper than usual into the world of, well, circles.
Circles, that's right.
Yeah, circles, but not just any circles. We're talking geometry here, the real nitty-gritty.
The beautifuls.
That's right. Beautiful, yeah. And, full disclosure, this one comes straight from you guys. One of our listeners sent in, I guess you could say, a very meaty math textbook chapter.
Very meaty.
Yeah, filled with all sorts of fascinating stuff about circles. And our mission, should we choose to accept it, is to unpath it all. Chords, arcs, angles, the whole 9 yards. We're going for that ha-ha moment, that crystal clear understanding.
Absolutely.
So circles, we got to start at the beginning, right? The core concept. What is a circle?
Well, a circle in its simplest form is just a collection of points, and all of those points are exactly the same distance away from one single central point.
Right, so equal distance from the center. Now, here's where it gets interesting. We can start drawing lines, straight lines, right, within the circle. These are called chords. And these chords, they start creating angles.
Right. And it's all about how those angles are formed and what relationships they have to each other. Your textbook has these great figures 9.1 and 9.2, and they show how a chord, let's say chord PQ, it can subtend an angle, meaning it kind of creates an angle at different places. So you pick a point R on the circle, somewhere on that longer arc made by PQ, and you've got angle PRQ. That's the angle subtended by chord PQ at that point R. Same chord, different point S on the shorter arc. Now you have angle PSQ, and of course the chord also makes an angle at the center of the circle itself, angle POQ.
Right, and here's something I noticed right off the bat, just looking at different chords. The longer the chord, the bigger the angle it makes at the center of the circle, right? It's kind of intuitive.
It is intuitive, and it actually leads us to our first theorem, theorem 9.1, which states that equal chords that are the same length, they're going to subtend equal angles at the center. And this works whether they're in the same circle or even in different circles, as long as the circles are the same size, congruent circles as they're called.
Oh, congruent circles. So basically like two identical cookie cutters.
Yeah, exactly. Two identical cookie cutters. And the theorem's saying that if you make the same cut in each cookie, the angles at the center will be the same.
I like that analogy. It's all about symmetry, right?
It is. And the textbook actually provides a very elegant proof for this theorem using congruent triangles.
Congruent triangles. Now you're talking my language. I love triangles.
Let's say you have two chords, A, B, and C, D, and we know they're equal in length. If we draw lines from the center of the circle, let's call it O, to the endpoints of each chord, what do we get?
Triangles. Two of them. Triangle AOB and triangle chord.
Right, and look at the sides. OA, OB, OC, and OB are all radii of the circle, so they're all equal.
All the same length because they go from the center to the edge.
Exactly, and we already said AB and CD are equal. Those are our chords. So we've got three sides of one triangle equal to the three sides of the other triangle. That's the side-side-side rule, SSS, for congruent triangles.
Yeah. SSS, that's a classic. If all three sides match up, the triangles are identical.
Identical twins. And since they're congruent, all the corresponding parts are equal. That's where the CPCT comes in. Corresponding parts of congruent triangles.
CPCT, love it.
So angle AOB, made by chord AB at the center, has to be equal to angle COD, made by CD at the center.
Okay, so equal chords, equal angles. Makes sense. But now let's flip the script. What if we know the angles at the center are equal? Does that mean the chords have to be equal?
Ah, you're thinking about the converse of the theorem. And, your textbook tackles this head-on with a really neat activity involving tracing paper.
Oh, tracing paper, always fun.
It is. So you draw two equal angles from the center of the circle. Let's call them AOB and POQ. You cut out the pieces of the circle those angles make, the segments, and guess what? They'll fit right on top of each other perfectly.
No way.
Yes, they're congruent. And if those curved slices are identical, then the straight lines that define them, the chords AOB and PQ, those have to be equal too.
So it works both ways. Equal angles at the center, equal chords.
Exactly. That's theorem 9.2. And the proof, once again, it's all about those congruent triangles, AOB and COD. This time, we start with knowing the angles are equal, AOB and COD. And we still have OA equal to OC and OB equal to OD because they're radii. So now the triangles are congruent by SAS, side angle side.
So it all comes back to triangles, huh? They're the building blocks of geometry.
They really are. Now let's shift gears a bit. Let's move from the angles at the center to something else. A line from the center to the chord itself. Your textbook has this cool activity where you fold a circle so that a chord, let's say AB, lines up perfectly on itself.
Like folding it right in half through the center.
Exactly. And that fold line, that crease, It makes a point where it hits the chord, we can call it M. And what do you notice about the angles and the segments of the chord?
Okay, so the crease, that's a line from the center, right, to point M on the chord. It makes two right angles with the chord, so it's perpendicular.
Perpendicular, that's the word.
And hold on, since we folded it in half, point A landed right on point B, which means that line, it cut the chord right in half. MA equals MB.
Bingo! You've just illustrated theorem 9.3. The perpendicular from the center of a circle to a chord bisects the chord.
Bisects, fancy word for cuts in half.
Precisely. And you can prove this with congruent triangles, those right triangles, OM and OMB.
Oh, those triangles again.
Always lurking. OA and OB are equal. Their radii. OM's the same for both. Right angles at M, that's what we call hypotenuse leg congruence, HL. So the triangles are congruent, and since they are, MA has to equal MB.
Because corresponding parts of congruent triangles are equal. CPCT.
There it is. You got it. But now the question is, what about the converse?
Converse time. Okay, so if we have a line from the center that cuts a chord in half, does it have to be perpendicular?
That's where theorem 9.4 comes in, and it says, yes, absolutely. If it bisects the chord, it's perpendicular.
Nice. Geometry just makes sense, doesn't it? It all fits together.
It does. It really does. And this one's proven with congruent triangles, too. Chord AB and midpoint M, so AM equals BM. Draw the line from center O to M. We got our triangles, OAM and OBM. OA equals OB radii. We know AM equals BM. And OM is the same for both. That's SSS congruence, side-side.
SSS strikes again. So the triangles are identical.
Identical, and because of that, the angles have to match up too. OMA and OMB, they're corresponding angles, and they're also next to each other on a straight line, a linear pair. If they're equal and on a straight line, they got to be 90 degrees each.
Boom. Perpendicular. It's all about those triangles.
It is. Now, let's talk about how far a chord is from the center of the circle. You know, your textbook actually defines this as the distance of a chord from the center, and it's simply the length of that perpendicular we've been talking about.
Makes sense. So in figure 9.8, it's the length of PM.
Exactly. And think about the diameter, the longest chord you can have. It goes right through the center, so its distance from the center is 0.
Makes sense. And just looking at it, it seems like the longer the chord, the closer it is to the center.
That's a great observation, and it's formalized in theorem 9.5. Equal chords are equidistant from the center, meaning they're the same distance away.
So if you have two chords that are the same length, they'll be the same distance from the center.
Precisely. And your textbook illustrates this with tracing paper and folding, showing those distances are indeed equal.
Okay, time for the converse, right? If two chords are the same distance from the center, do they have to be equal?
You bet. That's theorem 9.6. Chords equidistant from the center are equal in length. They even have an activity for this one, too, where you draw those equal distance lines, OL and OM, from the center, and then construct perpendicular chords. When you measure the chords, they'll be the same length.
It's all about that balance and symmetry, isn't it? Equal chords, equal distances, equal angles. It all ties together so beautifully.
It really does. Now, your textbook has this great example, example 1. It's got two chords, A, B, and C, D, and they intersect at a point E inside the circle. And we're told that they make equal angles with the diameter that passes through that point E. We need to prove that A, B, and C, D are equal.
Okay, so we've got intersecting chords in a diameter. Sounds like a geometry puzzle.
It is. And the solution, it's elegant. You draw perpendiculars from the center, AOL to AB and OM to CD. And because of those equal angles with the diameter and the fact that angles on a straight line added to 180 degrees, you can figure out that angle, LOE equals angle, MOE.
So we're using our angle knowledge here.
Absolutely. Now look at those right triangles, OL and OME. We've got those equal angles, LEO and MEO. And we just figured out LOE equals MOE, plus EO is the same for both triangles. That's angle side congruence, AS.
So the triangles are congruent.
And if they're congruent, their sides have to be equal. AOL, the distance of AB from the center, equals OM, the distance of CD from the center. But wait, theorem 9.6 told us that if chords are equidistant from the center, they're equal.
So AB equals CD. We solved it.
We did. Now let's move on from chords to arcs. A chord, unless it's a diameter, splits the circle into two arcs, a major arc, the longer one, and a minor arc, a shorter one. Now, what happens if we have two equal chords? What about the arcs they make?
Well, if the chords are the same length, the arcs should be the same too, right? It's like cutting equal slices of pie.
Exactly. And the textbook confirms this. Equal chords make congruent arcs, and the other way around, congruent arcs mean equal chords.
They go hand in hand. Now, the textbook talks about the angle an arc make at the center of the circle.
Right. The angle supported by an arc at the center, it's just the angle made by its corresponding chord at the center. So minor arc PQ, angle POQ. Major arc PQ, reflex angle POQ, the bigger one.
So we're basically extending the concept of angles from chords to arcs.
We are, and we already know that congruent arcs mean equal chords, and equal chords mean equal angles at the center. So it follows that congruent arcs also subtend equal angles at the center.
It all connects, doesn't it?
It does. Now, hold on tight because we're getting to another big one. Theorem 9.7. The angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle, and this works for minor arcs, semicircles, and major arcs.
Okay, so the angle at the center is twice as big as the angle on the edge of the circle made by the same arc.
Exactly. The textbook walks you through the proof, which involves picking a point A on the circle, drawing lines, extending a line, and using that exterior angle property of triangles. It's a beautiful proof.
And this theorem leads to another important one, right? Theorem 9.8.
You got it. Theorem 9.8. Angles in the same segment of a circle are equal, so if you have chord PQ, it divides the circle into two segments. Pick any 2 points A and C on the same segment, and the angles PAQ and PCQ, they're both subtended by the same arc PQ. Theorem 9.7 says they're both half the central angle POQ, so they must be equal.
Makes sense. And what about that special case, the angle in a semicircle?
Ah, yes. If PQ is a diameter, then the central angle is a straight angle, 180 degrees, and any angle on the edge of the circle subtended by that diameter, it's got to be half of that, 90 degrees. So it's always a right angle.
That's a handy one to remember. Now, what about the converse of Theorem 9.8?
Theorem 9.9, it says that if a line segment subtends equal angles at 2 points on the same side of it, then all 4 points got to be on the same circle. They're concyclic.
Concyclic, like a circle party.
Exactly. All 4 points are invited to the circle party. Now, let's talk quadrilaterals, specifically cyclic quadrilaterals. That's when all 4 corners of a quadrilateral sit on a circle.
They're all part of the circle club.
That's right. And here's the cool thing. If you measure the opposite angles of any cyclic quadrilateral, what do you find?
They add up to 180 degrees. It's like magic.
It's not magic. It's Theorem 9.10. The sum of either pair of opposite angles of a cyclic quadrilateral is always 180 degrees.
Amazing. And of course, there's a converse, right? Theorem 9.1.
Of course, if the opposite angles of a quadrilateral add up to 180 degrees, then it has to be a cyclic quadrilateral. It's the other side of the coin.
And your textbook has some great examples to illustrate all this.
Yeah, like example 2. It's got a diameter AB, a chord CD equal to the radius, and lines that meet at a point E outside the circle. We need to prove angle AEB is 60 degrees. And it uses equilateral triangles, right angles, and semicircles, and our good friend Theorem 9.7 to crack the case.
Clever stuff. And what about example 3?
Example 3 throws us a cyclic quadrilateral ABCD with a couple of angles given, and we got to find another one. It's all about using angles in the same segment and that 180-degree rule for opposite angles.
Okay, so we're really getting into problem solving now.
We are, and then there's example 4 with those intersecting circles and diameters. We need to prove a point lies on a line, and we do it with those right angles in semicircles.
And last but not least, example 5.
Example 5 gets pretty abstract. We start with any old quadrilateral, draw its angle bisector, and boom, we end up with a cyclic quadrilateral inside, all thanks to that 180-degree rule for opposite angles.
Wow, so we've covered a lot of ground here, from basic definitions all the way to complex theorems and examples.
We have, and for me, one of the coolest takeaways is how that simple idea of equal chords leading to equal angles at the center, it just expands outward. It explains so much about arcs, angles on the circumference. It's like this hidden code of symmetry.
I agree. It's beautiful. And that 180-degree rule for cyclic quadrilaterals, that's just mind-blowing. It really sets them apart.
Absolutely. And, this might seem like abstract geometry, but these principles, they're everywhere. Architecture, engineering, astronomy, it's all built on this foundation.
You're right. It's the underlying structure of so much of our world.
And here's something to think about. We've been exploring circles on a flat surface, but what about SPIEs? 3-dimensional circles.
Ooh, that's taking it to a whole new level.
It is. What happens to our chords and angles then? Do the same rules apply? What new challenges and discoveries await us there? It's a whole new world to explore. Thanks for joining us on this deep dive into the world of circles.
It's been a blast. Until next time.